Hi there, welcome to a video on a spreadsheet for calculating humidity, including the wet bulb temperature, using the Newton-Raphson iterative method in Excel VBA. Here are some contact details. The psychrometric equation allows water vapor pressure to be calculated from wet bulb temperature, psychrometric constant, atmospheric pressure, and dry bulb temperature. But what if we don't have the wet bulb temperature? We then need to calculate the wet bulb temperature using the psychrometric equation, but through an iterative process, because there's no published analytical method for computing wet bulb temperature using the psychrometric equation. And that is where the Newton-Raphson method comes into play. The Newton-Raphson method allows roots of an equation to be determined. We can take the E across to the right hand side so that we've got 0 on the left hand side, and then solve iteratively for the wet bulb temperature as a root of this equation. How does the Newton-Raphson method do this? It's based on a guess wet bulb temperature, say 1 degree Celsius. We evaluate the function at x equals 1 degree C. We draw a tangent line to that point, tangent to the curve, and we obtain an x-intercept. That intercept is the first estimate of the root of the equation, first estimate of the wet bulb temperature. We then reevaluate the function, draw a second tangent line, get a second intercept. Reevaluate the function, get a third tangent line, get a third x-intercept, and carry on the process until convergence set by resolution that the user specifies. The Newton-Raphson method is quite efficient and only about 5 iterations are required. And that has been implemented here in Excel VBA. VBA is a powerful tool that allows sophisticated calculations behind the scene, but allows the user access to those calculations at the cell interface. To access the code using a laptop, we type Alt function F11, and that shows you just some of the functions that I've used in VBA. We're not going to go into the detail of this, but we will look at in detail on how to access these functions at the cell interface. The spreadsheet uses custom views. That's a very useful way of navigating a fairly complex spreadsheet. To access custom views, we press Alt-VV, and if we look at, for example, the psychrometric constant, there are 4 values, one of 0.066 kilopascals per Kelvin or per degree Celsius when the wet bulb is aspirated and unfrozen, and various others depending on the condition of the wet bulb. Alt-VV again. Let's look at the theory and calculations. I've sometimes used names in the spreadsheet. Overlapping with this information in this video is the information on another video that I've posted on RHCALC, which gives more detail about the names that I've used and how to use those. The theory, we use the ideal gas law and its various forms to calculate some of the humidity parameters, and here are all the calculations that have been performed in Excel VBA. Here are the terms that are used, and these are the SI units for the various terms. Let's look at the inputs. The inputs for the various VBA functions are normally the dry bulb temperature, a wet bulb temperature, atmospheric pressure, and gamma, where the atmospheric pressure is in kilopascals. Alt-VV. Let's look at some of the outputs. These are covered mostly in the previous video on RHCALC. I'll just go through one. For example, the vapor pressure. We use the psychrometric equation. We specify T wet and T dry and atmospheric pressure and the cell for the psychrometric constant, and it calculates the vapor pressure in kilopascals. Alt V. Introduction to VBA. As we said, VBA allows sophisticated calculations at the cell interface. To invoke the relative humidity function, we type equals RH, a dry bulb temperature, a wet bulb temperature in degrees Celsius, an atmospheric pressure in kilopascals, 92.6, psychrometric constant, 0.066 kilopascals per degree Celsius or per Kelvin. Press enter and it will calculate the relative humidity. If we look at the VBA outputs, that's the one for relative humidity. For vapor pressure in kilopascals, we use the function equal VP, a dry bulb, a wet bulb, an atmospheric pressure, a psychrometric constant. Similarly, for dew point, we use TDP as the function, same inputs. Vapor pressure deficit, VPD as the function, dry bulb, wet bulb, atmospheric pressure, psychrometric constant. Density of water vapor in grams per cubic meter, dry bulb, wet bulb, atmospheric pressure, psychrometric constant. This is the iteration now, the Newton-Raphson iteration applied. T wet I, in this case it's a dry bulb, a relative humidity, atmospheric pressure and psychrometric constant. If we do not have dry bulb and relative humidity, but we have dry bulb and dew point temperature, 21.13 in this case, degrees Celsius, and then the atmospheric pressure and psychrometric constant, that will yield the wet bulb temperature. The mole fraction is in millimoles per cubic meter, so it's 1,000 times MF is the function. Same inputs as before with the wet bulb. The molar volume, dry bulb, wet bulb, and so on, in millimoles per liter. And then the mixing ratio in grams per kilogram is mix ratio. Enthalpy, dry bulb, wet bulb, atmospheric pressure, psychrometric constant, in kilojoules per kilogram. And then the heat index, because that operates on dry bulb and relative humidity, we have to type a relative humidity value here, 30%. We get a heat index. There's more detail on the heat index in the RHCALC video. Alt VV. I want to finish off with validation. From the University of KwaZulu-Natal Agrometeorology Instrumentation Mars System in Pietermaritzburg, South Africa, I've obtained for 2015 the hourly dry bulb and relative humidity values. From that, I've computed the iterative wet bulb, T wet I, with that dry bulb and that relative humidity. And let's copy that down for the entire year. It hasn't updated because I haven't indicated to automatically calculate the updates. To automatically calculate the updates, press F function F9, and you can see it going through the iterations 16-20%, and it's finished. So it's quite efficient, 5 iterations per hourly line. I've then calculated the vapor pressure from that dry bulb and relative humidity. I've recalculated the vapor pressure based on the psychrometric equation, dry bulb and the iterative wet bulb. I've computed the difference, and you can see the differences are extremely small. So that kind of validates the Newton-Raphson iterative method for computing the wet bulbs. I've then approximated the wet bulbs, the wet bulb measurement, based on a weighted mean of dry bulb and dew point weighted by delta and gamma. That method is commonly used, and that's in column J. In column K, I've got another approximation for the wet bulb using the Stoll 2011 method. and I've compared in two graphs the weighted mean method with the iterative wet bulb, which is regarded as the correct value, and you can see quite a bit of scatter here. With the Stahl method, there's less scatter, much less scatter, but actually greater bias compared to here. But the Stahl method would be preferred because of the reduced scatter. And then finally, this just shows the number of iterations in the Newton-Raphson iterative process. Here, this is the maximum water vapor pressure difference, the two water vapor pressures that I showed you, and after about 5 iterations, there's pretty good convergence to the wet bulb temperature. The resolution, this is a resolution of 0.5 set by the VBA program, 0.1, 0.01, and I eventually used 0.0001 degrees C as the resolution. Thanks for watching. Cheers then.